So in this lesson, we will learn how to apply the force and torque conditions that give static equilibrium to solve physics problems easily and with speed. So what we have here is a ladder that rests against a frictionless wall. But the pavement on which the lower end is placed is not frictionless. It is also given that the ladder's center of mass is 1/3 way up from the lower end, and a firefighter goes up the ladder to a point where she is at a distance of L/2 from this point, or you could say her center of mass is L/2 from the lower end. And with this information, we have to find the magnitudes of forces on the ladder due to 1, the wall, and 2, due to the pavement. So when solving such problems, the first thing to do is to choose the system we are working on. So here it is a firefighter and the ladder. The second step is to draw a free body diagram. So let us show the firefighter as a point mass, and then the gravitational force can be shown as mg here. Similarly, we can mark the downward force due to the ladder as small mg like this. The force on the ladder due to the wall is the horizontal force Fw, and this would be the only force on the ladder since the wall is frictionless. In other words, there is no vertical force on the ladder due to the wall on account of absence of friction between the wall and the ladder. Next, we consider the force on the ladder due to the pavement. And here, the force on the ladder would be one, a horizontal force, that is static frictional force, and let us call it Fp small f, and a vertical force, that is normal force or the normal reaction, and we will label it as Fpn. So now we are set to apply the equations that are conditions for equilibrium or balance of this ladder firefighter system. And the first one is that the net torque on the system needs to be 0, and the second is the net force on it should also be 0. So when both these conditions are met, we say the body is in static equilibrium. So let's write the torque balance equation first, and our choice of origin or axis about which to find the torques can be this. And why so? Simply because we can see there are 5 forces that can cause torque about any point that we decide to choose. So we can choose this point as the axis of rotation, or this, or maybe even this. But if we choose this point as the axis of rotation, we see there are 2 forces that pass through this point. And by placing the axis here, we eliminate both these forces from the torque calculation, because by doing so, the distance of both these forces becomes 0 from the axis of rotation, resulting in 0 torque. So our axis would be at point O, and you should visualize that this axis would actually be perpendicular to your screen. That is, if the system was allowed to freely rotate, it would rotate about this axis. Now we can find the torque about O using the equation torque is equal to R perpendicular F, where R perpendicular is called the moment arm. And we'll just refresh our memory what moment arm is in a short while. So let us start with Fw, or the force from the wall. And here the moment arm R perpendicular of this force can be found by drawing a line of action through that vector and finding the perpendicular distance between O and the line of action, which is this. And this is the general way how you find R perpendicular for any force. That is, extend the line of action of the force and draw perpendicular from that line of action onto the point about which you have taken the axis of rotation, and that distance gives you R perpendicular. So here you can see that R perpendicular is the height h. In the same way, we draw line of action for mg and find that its moment arm lies along the x-axis. And since this length is a, the moment arm would be a by 2 for this force, because the firefighter is halfway up the ladder, and that is the reason this is a by 2. I mean, this is simple geometry that you can check on the side. And in the same way, we find that moment arm for this force would be a by 3, since the ladder's center of mass is 1/3 of the way up the ladder. And finally, the moment arm for this force and this force will be 0, because these forces pass through the origin. Now we can write torques for various forces in this form, and also remember that counterclockwise rotation corresponds to a positive torque and a clockwise rotation would be a negative torque. So the first balancing equation becomes minus h into Fw plus a by 2 into mg plus a by 3 into mg plus 0 times Fpf plus 0 times Fpn should equal 0. So when you solve for force due to wall, we get Fw is equal to Ga m by 2 plus m by 3 divided by h. And here a is root of L square minus h square, which when you calculate equals 7.58 meters. And this gives Fw as 407 newtons. Now we can go ahead and use the second equation, or the force balancing equation, and this gives us in the x direction Fw minus Fpf should equal 0, or Fpf should equal Fw, or 407 newtons. Also, the equation in the y direction Fnet y should also equal 0, and this gives us Fpn minus mg minus small mg should equal 0, or Fpn should equal m plus m into g, and when you calculate, you get this force equals 1146 newtons. So here is a quick step-by-step strategy for solving problems related to equilibrium in physics. Step 1 is, for an object in static equilibrium, starting point should be the recognition that net force on it should be 0. That also means along any x, y or z axis. Similarly, net torque about any axis must also be 0. Step 2 is draw a detailed free body diagram. Represent all the forces acting on the object. Label each force clearly, example, the normal force, tension, friction, weight, and so on. Then choose an appropriate coordinate system, which basically means finding the axis of rotation where most number of forces pass through to eliminate torque calculations as much as possible for those forces. Step 3 would be to break forces into components if needed. So as an example, for inclined planes or angled forces, resolve forces into x and y components. Step 4 would be to apply Newton's second law in the x direction. So set up sigma fx is equal to 0, and then use this to solve for unknown horizontal forces like friction, tension, etc. Step 5 would be to apply Newton's second law in the y direction. So set up sigma fy is equal to 0 and use this to solve vertical forces like normal force or support force, etc. Step 6 would be, if required, apply torque equilibrium. That is, sigma torque should equal 0 to solve for rotational equilibrium conditions. That is, clockwise and counterclockwise torque should balance or cancel each other out. Step 7 would be to solve the equations first algebraically and then plug in the values to get an answer. And finally, step 8 would be to think through if your answer aligns with your physical intuition. Like, are the directions and magnitudes of forces that you've calculated reasonable, or they seem out of place? If they do not seem reasonable, revisit the equations you've written and the assumptions you have made.